Very often a designer can satisfy their design objectives in more than one way. So a good example of this is shown here with these three different designs of a stanchion plate. On the left we have a fabricated assembly that's made from sheet metal and standard parts all welded together. In the middle is an aluminum extrusion that's been machined, and on the right is a casting. So each one of these parts is designed quite differently from the others, and that's because the manufacturing process used to make each of these parts has a profound impact on the part's design, and you can see that. The fabricated plate looks nothing like the extruded plate, and neither of them looks anything like the casting. And that's entirely because they're made by different manufacturing processes. So it has nothing to do with the actual function of the parts. Each one of these designs will work properly when placed into service in the finished product. In order for a designer to be able to begin their design work, they have a decision to make. So they have to decide what they're going to design. And that means they're deciding on the manufacturing process for their parts. Before they can even begin design work, they've made an important decision that locks in a really big proportion of the total part cost. So it's very common that design objectives can be satisfied in more than one way. A lot like this situation we're looking at here. And under those circumstances, a designer really should be interested in figuring out which approach is least expensive. So they want to satisfy their design objectives with the least expensive design. A useful tool that solves this problem by helping designers estimate the cost of their designs really early in product development, even before design work has even begun, is our Dfm concurrent costing software. In version 4 of the software, we've researched, developed, and added a brand new metal extrusion process, and I'm going to use this new functionality to analyze the aluminum extruded plate shown in the middle here. So this is a lower volume part. We're going to be making about 2,500 of those. And I'm going to import a CAD model of this part. I'm just going to import the extruded plate. And this is the part that we'll be analyzing in this video today. So this part is a non-rotational part, and it's hollow. So I'm going to choose this hollow block envelope shape. And you'll notice that the average thickness of my extruded part, so the thickness of its wall, is just about 2 millimeters. So I'll click the Select Process and Material button. And on the left, I'll choose Metal Extrusion. I'm going to assume production in North America. And the strength of this part is actually pretty important. So I'm going to choose a medium strength aluminum alloy. I'm going to choose this 6061 aluminum. And when I click OK, the software generates a default manufacturing process that includes the extrusion, an artificial aging process, and the secondary cutoff. So based on that process, the software generates a default estimate of my part cost, which includes the selection of the optimal minimum cost machinery from the software's machine library. So that this software is set up so that the main response panel here, shown on the right, it displays all of the important cost drivers for the metal extrusion process. So these are all of the things that are important to consider when estimating the cost of an extrusion. And all of that information has been defaulted based on either the CAD model that we imported or typical reasonable values. So based on that, my initial cost estimate is about $2.43. including a tooling cost of about $2,200, which gets amortized over my life volume. So I can get a reasonable idea of a part's cost just by specifying a life volume, importing a CAD model, picking a manufacturing process and a manufacturing location, and then specifying a part material. Next, I'm going to go through all of these primary cost drivers, and I'm going to make any modifications that I think might be needed. So basically I'm going to refine that initial cost estimate. And everything seems to look pretty good so far. So this finished extrusion is going to be treated to a T6 temper designation. It's going to be made from a 6061 T6 material. So the part is going to be cut off, and the ends are going to be cut square with a 90-degree angle. The wall thickness is uniform. It doesn't vary in thickness. And the cross-section is hollow. So this external perimeter, I'm going to use the CAD model to define that information. So I add the edge length to my geometry calculator, and I'm going to define the external perimeter here. So I'm just going to go right around the outside of my part, right around the outside of the cross section. So we've selected the perimeter shown here in red. So this cross-section has a single hollow void in it. So I'm going to enter a 1 for the number of extruded voids. And then I'm going to use the CAD model to define the internal perimeter for this part. So I'm going to add a edge length entry to my calculator again. And then I'm going to define the perimeter right around the outside of my internal void. So I'm defining the perimeter shown here in red. And my cross-section has no sharp corners, so I'm going to uncheck both of those checkboxes. And now I've been through all of these major cost drivers, and my analysis of the extrusion is complete. So the extrusion is solution treated during the extrusion process. It's aged and then cut to length. And then refining that initial cost estimate, it decreased my cost results by about 13 cents or so. So the extrusion prior to finished machining actually costs about $2.30. With the tooling, that costs about $2,000. So in version 4 of the software, we've added a brand new process simulation feature. When I click that process simulation button, the software launches its simulation. So internally, the software is extruding a billet of material. It's extruding it mathematically, and then it optimizes all of the extrusion process parameters for the specific part that we've just analyzed. And it's, I should probably mention that this method of optimization that the software uses to generate all of these optimized results, it's been patented. So after the software goes through its optimization process, the optimal billet preheat temperature for this part is 459 degrees centigrade, and the optimal length of the billet, the one that minimizes the cost by making the best trade-off between material and processing costs. That's 965 millimeters. And my optimal exit speed is 0.215 meters per second. And extruding under those conditions results in an exit temperature of about 521 degrees centigrade. And we can see that more than half of the temperature increase due to extrusion is due to the adiabatic deformation of material. So about 35 degrees centigrade of that temperature increase is due to adiabatic deformation. So the temperature of an extrusion, usually it's not constant throughout its cross-section. And pretty frequently there's a temperature gradient that exists in the extruded cross-section. And we can get a pretty good idea of what that temperature gradient looks like for this part based on this theoretical depth of the heated surface here. So here we can see for this part that this exit temperature of 521 degrees centigrade, that heated layer of material, it ends up in a layer on the surface of the finished extrusion. And that layer is just under 1.3 millimeters thick. So the heated depth, this 1.3 millimeters, that's just over half of the wall thickness, which is 2 millimeters. And what that means is that this part is going to have a very small temperature gradient after it's been extruded under these optimal minimum cost conditions. And really, that's kind of important to know because it tells us that the mechanical properties of this extrusion will likely be quite uniform. So the quality of this part is likely to be very, very high after the extrusion is produced. And that's the type of helpful information that you can get from this simulation. So the cost of the extrusion prior to finished machining is $2.30, and about $1 of that is in the material cost. 25 cents is due to setup costs. There's almost 21 cents in the processing cost, and rejected parts, they add just about a penny. And that results in a piece part cost of just about $1.48. And our tooling costs are just under $2,100, which amortizes out to almost 83 cents a part. And that all totals out to that $2.30 per part. So with the DFM concurrent costing software, you can learn and understand a significant amount of cost-related information about your part. And you can do that while starting out with some very simple information and some very common knowledge about your part. So there's no detailed design work required. I hope that you found this helpful, and in my next video I'd like to show how the secondary machining operations that are done on this extrusion are included.